Hey friends, welcome back to another video. It's me, Ashel the Brilliant, and you're watching Learn with Ashel. And today we're going to be learning the theorems which we use on triangles, which involve the projection of the sides of triangles. And this first theorem that we're doing is theorem 1. It's for obtuse triangles. So we apply it on obtuse triangles, that means. And the theorem states that the square of the side opposite to the obtuse angle, let me just draw the triangle as well, so you can see it as well. Yeah, so let's say that this is the base, and let's use oh no, not this. Yeah. Now, let's just choose this. Okay, so I'm making all the sides different so that it's easier for you guys to understand exactly what we're talking about right now, right? So, here we go. This is a triangle, and I'm going to name it triangle ABC, and it's an obtuse triangle because you can see right here that this angle is obtuse, this angle B is obtuse. It's clear, right? It's bigger than 90 degrees. Anyway, what is our theorem? The theorem is that the square of the side that's opposite to the obtuse angle. So now that we've drawn our triangle, let's see how it goes. So over here, the square of the side that's opposite to the obtuse angle, so this is the obtuse angle, the side opposite to that is the side right here, AC. So AC square is equal to the sum of the squares of the sides forming the obtuse angle. So the sum of the squares of the sides that are forming the obtuse angle, which sides are forming angle B over here, ABC? Which two sides are forming that? The side AB and BC. These two sides are forming the obtuse angle, so they're the sum of their squares. So the squares are like AB squared and plus BC squared. That's their sum, along with twice the length of one side and the projection of the other. So you see, we don't really have the projection right now, do we? So what is the length of one side and what is the projection of the other? So the length of one side you can take is as AB's length, so plus 2AB into BC, which is the other side. But we're not going to write into BC because that's not the projection. We need the projection, you could say, on the x-axis, right? So to get that projection, we're going to have to do some construction, and then we'll be able to complete the theorem. So if I do the theorem right now it would look like this: AC squared, this is the side that's opposite to the obtuse angle, right, is equal to AB squared, which is one side, the sum of the squares of the side, so AB squared plus BC squared, this is the other side, plus 2 into AB along with twice the length of one side. So the length of one side is into AB and into what? It can't be BC. It has to be a projection of it, right? But what do? We don't have the projection. So we do construction. So now to get this projection, I'm going to do some construction, and yeah, we'll get the projection. So construction, maybe just erase this a bit. Construction. Okay, so they're up and down, but okay. What is the construction? So we're gonna do the construction right here. I'm just gonna write what we're gonna do as well. So we're gonna draw a perpendicular from point C onto AB, there, onto AB, touching a point called D. Now, you don't have to do it exactly like how I'm doing, right? Your triangle could be PQR or something, or STU or something, right? And you're like this point. I'm just naming this point. I'll show you right here when I draw the projection. So let's use some good colors. Yeah, what good colors do we have? But anyway, right. Let's just stretch this. So here I'm gonna like actually, yeah, this I should have done C first, but yeah. So this is the projection by, like, this is the perpendicular there. Now it's straight. So this is the perpendicular from point C, and I'm just gonna, oh my bad, there. And yeah, okay, and let's just make this a little dotted too. Whoa. Yeah. Yep. So right here, let's just draw a little bit. Yeah. So now it looks okay. It looks livable. So let's just call this point of intersection from, like, the perpendicular, the point of intersection of, like, perpendicular C onto AB, where from point C. So like we're gonna call this point D, right? So this piece right here, where is another good color? Just use this. This distance is the projection of this side BC. Right. Now, we have our projection, so let's go and put it in. The projection is BD, as you can see, right? Because, like, that's, you could say, like, projection is type of like a shadow, right, of that side. So like BC, its shadow is BD, we can say, on the x-axis. So yeah. Now we have the theorem. This is the theorem, right? And now it's time to actually prove it, right? So how are we going to prove it? First of all, I want you to come over here into this image. Maybe we could, yeah, like, I think this much zoom is enough just for now. I just want to show you something real quick. So what should we choose? Well, let's just choose red, or maybe it's already chosen. So yeah, let's just choose this, whatever. So this triangle, you can see that now we're proving it, okay guys? So like, pay attention here. We are gonna look at this triangle as a right triangle, as you can see, if once we've drawn the what is it called, base. Then like this becomes like the base in a right triangle, and this becomes like the perpendicular, right? And this is like the hypotenuse, so this becomes like a right triangle. And if you look again, you can also see that there is a smaller right triangle, BDC. There's ADC, the big one, and BDC, the small one. They're both right triangles, and we're going to use these right triangles, actually, if you didn't know, to prove this theorem. So how are we going to do that? Let's begin. So like, we're going to start off by first reviewing the PGT, or the Pythagoras theorem. If you guys don't have any idea what I'm talking about, I'm just gonna give you like a quick recap like of what the PGT is, right? So the Pythagoras theorem is that it's applied to right triangles, and what it states is that, if we go back here, this is consider ADC, right? It's a right triangle. What it states is that this is like the hypotenuse. This is called the hypotenuse in a right triangle. The parts are like called like this. This is like the base, this is perpendicular, and this is the hypotenuse. AC is the hypotenuse. So AC is the hypotenuse. It states that hypotenuse, the square of the hypotenuse, so go down here, states that the square of the hypotenuse, oh, maybe I should just draw this again. right, like this. The square of the hypotenuse is equal to the square of the base, which in this case in ADC, right triangle ADC, it's AD. So the square of the base, so AD square, so B square I'm going to say over here for now, plus the hypotenuse square is equal to, or is the sum of, the square of the base and the square of the perpendicular. In this case, that's CD. So we're going to say P for short, right? Like for perpendicular. So yeah, like we can even write it like this: H square, or actually not H square. I mean, I'm just telling you what the hypotenuse is. This is the hypotenuse. This is the base, and this is the perpendicular with P. So now we also have BDC, so we're going to take both these right triangles, right, and we're going to apply the PGT on it. So we're on them. So we're going to say apply PGT on both right angle triangles, which are right angle triangle ADC. This is the big one. And right angled triangle BDC. So let's go up here. Let's take right triangle ADC. ADC is like the hypotenuse of ADC is AC, right? So AC square is going to be equal to the base. What is the base? Base is AD. So AD square plus the perpendicular square, which is CD. So CD square. So AC square, let's say in right angle triangle ADC, AC, the square of AC is equal to the square of AD, which is the base, we said, AD square, plus the square of the perpendicular, which is CD. So AC square is equal to AD square plus CD square. And we can let this be equation number 1. Now let's go back. I just want to show you as well so that you have an idea of what we're talking about. Hopefully you know what we're talking about by now. So like BDC, the hypotenuse of BDC is BC. So BC, its square is going to be equal to the base, which is BD in BDC. BD square plus CD square. The perpendicular is the same as the perpendicular for ADC because, yeah, you know, they're both at the same place, kind of. Just the hypotenuse are different and the bases. Anyway, yeah, so BC square is equal to BD square plus CD square. BC square, oh, let's actually just write it as well. In right angle triangle BDC, BC is the hypotenuse, so its square is equal to BD, which is the base, plus CD, which is the perpendicular. Let this be the second equation. Now I want you guys to come back here and look at it. Look at it. AD, and go back to this equation. Like, you can see we have AC square in this equation, right? And that's what we need. Like, go up to the theorem. What is our theorem that we're proving? We're proving that AC square is equal to something, something, something. So AC square, whichever equation has AC square, that's the one that we want to change something in, right? That's the one we want to be dealing with. So AC square is in equation 1. So let's change something in equation 1. So now, like, if we come over here, CD is the perpendicular, and we know it's not going to change, right? But AD, we know something about AD. We know that AD, yeah, let's just use this color. AD is equal to AB plus BD. Do we not know that, guys? Of course we do, right? So AD is equal to AB plus BD. And we're going to replace this in the first equation so that we get things moving and we get something, right? And like then we'll use the second equation as well. So we're going to say that since AD is equal to AB plus BD, we're going to say replace in equation number 1. So what we're saying is replace AD with AB plus BD, and now you'll see what happens when we do that. So we have AC squared is equal to the AD squared, which like we're replacing, right? So we're replacing with the AB plus BD, so it'll be AB plus BD whole square, as it was AD squared, plus CD squared. We know that this was just there from there. And yeah, now what we're gonna do is expand this square. So AC whole square is equal to AB whole square. This is like the A plus B formula, A plus B whole square formula from pre-algebra. I'm pretty sure you already know it, right? So yeah, it's AB square. So like this is like A, this is like B. So A square plus 2 into A, which is AB in this case. This might be a little confusing maybe because I'm saying A into B type of thing. But like yeah, AB, which is A, so into B, which is BD. So 2AB into BD plus BD whole square as well. So that's like B squared, this is A squared, this is 2AB, plus CD squared. This was, you know, already there, right? Okay, so we're gonna call this equation number 3, and now you can see that we have now we haven't really used equation number 2, right? So we're gonna basically use that now. So like I want you to take a good look at equation number 2. That is BC squared is equal to BD squared plus CD squared. Now when you're done, come back to this equation number 3. Look at it. AC squared is equal to AB squared plus 2 into AB into BD plus BD squared plus CD squared. Do you see anything familiar? Anything common? I think you do, because I do as well. I see that BD squared plus CD squared is common in both equations, and I also see that in equation number 2 it's equal to BC squared. So what I'm thinking, if you're thinking what I'm thinking that we should replace, not just keep on thinking. I think we should just replace BC squared in the place of BD squared plus CD squared. Let's replace it with BC squared. Come on. So right here. So we're gonna say since yeah, so BD square plus CD square is equal to BC square. Replace. That's all we're gonna say, and that's enough. So let's do it. AC square is equal to AB square plus 2 into AB into BD plus BD squared plus CD squared we're replacing with BC squared. So this is what our end result, or you could say our theorem, looks like, and basically we've proved it. And if you don't really think so, then let me just go up there and grab our theorem. This is what we said the theorem was. Why am I switching to the eraser? We need the selector tool. So yep, and let's come back down here and let's compare them. So right here you can see we have AC squared, we have AC squared and AC squared, and we have AB squared and AB squared, and we have 2AB into BD, we have 2AB into BD over here, and BC squared, we have BC squared right here. So there we have it. We have proved this theorem, and yeah. If you have any questions, confusions, or anything that you don't get or something, you can always leave a comment in the comment section, because I'll get back to you. No worries. And I know that you learned something today, and I hope that you repeat it. If you repeat this several times, you'll get the hang of what is what and why it is like that, right? And once you get that, it's nothing. These theorems, they're usually really dawned upon, and everyone's like, oh no, frowned upon. Everyone's like, oh no, theorems, oh no, I don't understand. Why does this theorem say this, or what do I do in this theorem? How do I solve this theorem? This and that. It's really simple, honestly. I'm really honest with you guys. If you understand why you're doing it, why it's happening like that, you'll understand what you need to do. You won't ever get confused oh, what do I do here? How did he do that? How did he get that? You won't ever get confused like that. So yeah, that's my tip, that's my advice, and yeah, for more videos, subscribe to the channel because I'm gonna post videos every week. Yeah, because I kind of have a busy study schedule, but yeah, I'm gonna try pumping out videos every week, and the next video I think will be about the second theorem, which is for an acute triangle. So yeah, subscribe and like if you found this helpful, as it'll help other people find it. Share it as well so that it helps other people find this video. And yeah, until next time, peace out.